Yeah, thanks everyone for coming. So my name is Charles Jin, and today I'm going to be presenting neural architecture search using property-guided synthesis. This is joint work with Menko Potilam-Tanam and Sudip-Roy. So let me start first by providing some background on why we, as programming languages people, should care about neural architecture search, or NAS for short. So this figure here shows ImageNet accuracy over the past decade, and starting in 2013, we have AlexNet, which sort of started the modern deep learning revolution, and that is indicated by this cloud of points over here on the right, which looks excessive, but it did give us, ChatGPT eventually, which I think is a hot topic right now. And traditionally, developing new architectures has relied heavily on human ingenuity, a less flattering description of which might just be trying a bunch of stuff and praying. So starting around 2013, researchers began looking to automate aspects of architecture search. So for this work, we're going to adopt an evolutionary approach to NAS because it is one of the few approaches that will actually let us search the full space of neural architectures. In evolutionary search, the central data structure is the population. And here we've initialized the population with a vision transformer and then also run one generation of evolution again, so it contains two architectures. And just for illustrative purposes, the fitness that we're going to use here is accuracy, but in general, it might contain some other objectives as well, such as latency or memory. So the first thing we're going to do is select an architecture from the population, preferring those which are more fit, and this one we're going to call a parent. We're then going to mutate the parent to create a child, evaluate the child for fitness, and then insert it back into the population, which concludes this generation of evolution. So each generation, we get one new architecture. We run this in a loop until we've exhausted our computational budget, and then we sort of terminate the search and return the best one as the output. So that's evolution at a high level. Now we're going to look into specifically some details. And I want to start first with the search space, because that's probably the most important part of this whole thing. We're going to be representing architectures over here on the left as a sequence of blocks. And so here you have like a CNN, and it's got 3 copies of block A followed by 2 copies of block B and so on. And then on the right, you see that each block defines a different graph computation. And so the nodes in this graph are just neural network operations, and the edges are the data flow relationships. And so we're going to view these computations as programs in a DSL, where essentially the primitives are just these neural network operations like convolutions and ReLUs. And the grammar just ensures that each node in the graph has the right number of inputs. So it's a very flexible grammar. And in particular, for our search, we're going to use 1,800 unique OPS, which can be composed into these arbitrarily complex graphs. So it's a pretty big search space. I also want to mention on the left, this block-based representation, for some of, if you're not aware, is like a very common thing to a way of specifying neural networks, because it's more compact, so our puny human brains can understand it better. But obviously you can convert a sequence of blocks into a single graph. And so I'm sort of just going to equate the search space with these graphs and the rest of the talk. All right, so clearly this block-based thing is going to provide us an inductive bias for the search. And so the first thing we're going to do is extend the selection phase of the algorithm with this block-based representation as well. So once you have the parent, you select a block within the parent. And here this box block is a subgraph within the block that we've selected for mutation. We're next going to mutate the block by mutating the subgraph within it. And here I've illustrated this subgraph mutation with a singular arrow, but I want to emphasize this is not an accurate representation of what we eventually do, but I'll be coming back to this point shortly. So now we have the mutated block, and we're going to insert it back into the parent to create a new child architecture. And we do this by replacing random instances of the old version of the block with a new block. So that gives us a new generation of the CNN here and completes the mutation of the architecture. And then to complete the loop, we evaluate it, insert it into the population as with before. So I want to come back now to this mutate step. That's it for the background. I want to come back now to this mutate step, because if you think about it, this is really the important thing if you think about evolution as a search algorithm, because that's actually where the new architectures are being created. And if we were running vanilla evolution, the thing you would do is just sort of randomly mutate the subgraph that you've selected, because that's what evolution does. The thing is, and this is actually what the prior approaches do, but specifically in neural architecture search, there's like a huge problem here, which is that if you want to mutate randomly, you're stuck doing these very small mutations, which means very slow exploration. And the reason is that this random exploration policy, as you select bigger and bigger subgraphs for mutation, gets stuck in this bad local minima. So we can sort of understand this with this example here. Here I have like 3 mutations, none of which really look like good ones, right? So the first one is just a sequence of activation functions. The second one is a sequence of convolutions. The last one has no trainable parameters. And while these mutations might be useful in certain situations, if you're selective about where you put them, if this is what your average mutation looks like, if you're doing things randomly, you're going to end up with this population of things that I would hesitate to call architectures. They're legal programs in your DSL, but they're not really deep neural network architectures. So we're going to call those architectures degenerate architectures. So why does this happen? Remember that our search space is basically just any computation graph you could write down. And so if you select a random one, the vast majority of legal computation graphs are not going to look like actual deep neural networks. And so this is the problem of the search space being very sparse or jagged. And so in the same way, if you increase the size of the random mutation, you're essentially creating like a very small random architecture and then plugging it in as a subgraph. And so you have the same problem. And so I think another way of putting this is that good architectures, which you would consider to be deep neural networks, contain a lot of structure that is not present in the DSL. So in this work, we propose to capture the structure using abstraction, and we're going to call our approach αNAS. More specifically, our main idea is to guide the search away from degenerate architectures by mutating abstractions instead of the concrete architectures directly. So whereas prior works rely on these random mutations performed directly on the concrete architectures, we're instead going to perform our mutation in 3 steps. Starting from the subgraph selected for mutation, we're going to first abstract the subgraph into a set of properties. We're then going to mutate in the abstract space. And then finally, we're going to concretize the mutated properties back into a satisfying subgraph using program synthesis. So the key is that instead of performing the mutation step directly in the concrete space, we're first going to go through this, our exploration mechanism is kind of lifted to this abstract space instead. So for the next portion of this talk, I'm going to be introducing the properties we use as well as how to compute the abstraction function efficiently. And when I say efficient, what I really mean is we want to use static analysis. The reason being, if you compute these abstractions using dynamic analysis, you have to compile its subgraphs, which takes on the order of a few seconds. And during concretization, we're actually going to call abstraction in a loop that executes like thousands of times, which ends up being like hours of overhead per generation. So we'd really like to avoid that. Okay, so the first 2 abstractions are pretty easy. We care about deep neural networks, so it makes sense that we're going to have a property capturing depth. And so we just define the depth to be the maximum number of alternating linear and nonlinear operations on any path between each input and output. And so this figure gives you an example, and clearly this can be inferred statically and efficiently using any longest path algorithm. The next property is the shape property, which just tells you what the input and output shapes of the original subgraph were, and this is sort of like a type signature. And it's essentially just going to ensure that when we plug in the synthesized subgraph, it still gives us a well-defined computation. So to infer this, we can just leverage the built-in shape inference of JAX, which is the underlying ML framework we use. So this last one is a little bit more involved, and it's called the mixing property. And what it tells us is how the information is mixed as it flows from an input to the output. So the easiest way to understand this is with a few examples. So if you think about a convolution, as the input passes through the convolution layer, there's some local mixing of information going on that's given by the kernel of the convolution. On the other hand, if you think about pushing the input through like a transpose operation, for instance, which is an operation that just permutes the dimensions of the input, you don't have the same sort of entangling of individual elements, but you do sort of twist the input tensor. And so that's the kind of information that we're going to want to capture with this. And so over the next few slides, I'll be building up to a formal definition using this 3x3 convolution as a running example. Okay, so we're going to separate it into 2 subproperties. The first one is the pairing subproperty, and this is going to give us coarse-grained information about the correspondence between input and output dimensions. And this is the one that's going to help us understand how the transpose twists its input, for instance. So on the left here, this highlighted row is the height of the output. And to compute this, what we're going to do is take a slice of the output tensor on the height dimension, and then look at its pre-image in the input tensor. And when I say pre-image, what I mean is when you compute this slice in the output tensor, you need to access these elements in the input tensor. And so what we see is that when you're computing the output slice, you have to access at least one element along every position of both the channel and height dimensions. So in other words, the pre-image contains a slice of both the channel and height dimensions of the input tensor. And so we're just going to put a 1 in the height and the channel columns on the left and a 0 in the other two. The same thing for the channel column. We're going to take a slice of the channel, look at the pre-image, and we see that only the channel dimension in the pre-image contains a full slice. So we put a 1 in that column and a 0 in the other ones. And so I'm leaving out some details here, but hopefully this diagram makes things a bit more clear than what I can say. And we also see that if you were to do this, infer the pairing property for a transpose operation, what you're going to get is actually exactly the permutation matrix corresponding to how the dimensions were swapped. So the second subproperty is the locality subproperty, and this is the one that's going to tell us what the shape of the linear kernel is. And importantly, what it's going to do is tell us that the dense layer is less expressive than a convolution layer, for instance. The reason being a dense layer you can really view as just a 1-by-1 convolution. So it's a special case of convolution, and therefore we want to capture the fact that it's less expressive if you use it in your neural network. And as with before, what we're going to do is look at a pre-image, but this time we're looking at the pre-image of a single element in the output tensor. So the first thing we're going to do is that if the locality was x in the pairing, or the locality, we're going to put an x anywhere the pairing was 0. And then there are 3 other types of symbols here. The m stands for many to 1. So we see that the input tensor has a many to 1 relationship in the height column, in the height dimension here. And there's 3 elements contributing to the computation of 3-by-3 convolution. That's more than 1, but less than all, so many to 1. The same thing with the width column. We just put an m in the only entry that wasn't already an x. And then this last one, for the channel dimension, you see a full slice. So we're going to put an a there, and that happens to be, all of the entries. And yeah, so I should mention on the previous slide, like if you had done this for a dense layer, for instance, you would have had an 1-to-1 in both the spatial dimensions. And so if you can basically write down this partial ordering on this property, and that'll tell you that the dense layer is less expressive than the convolutional layer. Okay, so putting this all together, the mixing property gives us this coarse-grained information about how the dimensions are paired, as well as this fine-grained information about the shape of the linear kernel and the specific computation that's occurring within it. And so the good news is we can compute the mixing property using the built-in autograd engine that's like standard now in deep learning. The bad news is that running autograd is inherently dynamic analysis because you have to compile it, so that's bad. So to get around this, we're going to define an abstract interpretation for the mixing property. And what this is going to allow us to do is we're going to basically lazily evaluate and cache the mixing property for each unique op as we see it. And then when we go to infer the mixing property for a subgraph, we're going to abstractly interpret it and get an over-approximation. And the over-approximation turns out to be like in the right direction for what we want to do. But I'm not going to go into any more details here. So please take a look at the paper if you're interested in the full analysis. Okay, so that's it for the abstractions, and obviously the next question is how do we concretize? So how do we invert the abstraction? And I want to emphasize that clearly enumeration is not going to work for us here because we have 1,800 operations in our DSL. Here we have a mutation that has depth 4, and so you need at least 4 elements. That's already 3.8 billion subgraphs to enumerate through, so we can't do that. So to address this challenge, we introduced progressive synthesis, which is a new efficient algorithm for program synthesis. And formally, what we're going to do is, during synthesis, we're going to start with the identity program and then apply a sequence of transformations until the program satisfies the desired properties. So the key is to just identify what sequence of transformations you want to apply. And here, our programs, again, are computation graphs, and the transformations we apply are just going to be appending operations to them. So it's pretty obvious that you could do this for depth alone. It's not so clear for mixing. And here we basically devised a general framework that allows us to prove convergence and efficiency in general. So the key is to define a distance function first, which conceptually tells you how far you are from satisfying the property. And basically, it's just going to return a positive number such that it's 0 when the property is satisfied. And the other thing that makes this work is that you also want a set of to identify a set of transformations such that if you're given a program in any feasible property, you can always find some transformation within it that will bring your program closer to satisfying the property. Yeah, now synthesis is easy, right? Because at each step, you just try every single transformation in this covering set. You pick one that makes progress, and then you append that. And then you can just loop until the distance is 0, and then you're done. And so, clearly this solves the synthesis problem in linear time, which is great. The difficulty, obviously, is in, first of all, identifying this covering set, proving its covering, and being able to find an efficient way of computing the distance. And so I think the obvious question remaining here is like, what if there's some great property that you care about and you can't find this distance function, or there's no the covering set is too big or something like that? So we explore one answer to this question in the paper by defining the class of recursively consistent synthesis algorithms, and which happen to be exactly as powerful as progressive synthesis. So if you can solve the problem via recursively consistent means, then you can find this distance function and the covering set and apply progressive synthesis and get polynomial time synthesis. And what I mean by recursive consistency is that the algorithm doesn't have to write down the entire solution in one go. So there are some natural stopping points along the way from which you can sort of like go to sleep, come back, and still be efficient from that starting point. So for instance, if you're writing a program, maybe you write a function, break it down into modules first, or if you're trying to prove a theorem, you can write down some definitions and prove some lemmas before you do the entire thing. So recursive consistency really breaks if it's like I write down a partial solution and I come back to it and I have no idea how to use that solution, right? And so I like to think about recursive consistency as a structural constraint on the interaction between the semantics of the problem at hand and the language of transformations you have to compose a solution. And so we have a series of results in the paper that I think shed an interesting perspective on when we can expect synthesis to be efficient in general. So that's all I'm going to say on this topic for now. And in the interest of time, I'm not going to actually provide the construction of like the distance function for mixing and how you can even combine them, because that's not clear either. But yeah, again, please take a look at the paper if you're interested. Okay, so the last question that I think is in everyone's mind is like, okay, you have this like synthesis abstraction thing, but why does it work? And so here we're returning back to the figure from before, which was like the motivation for like bad mutations. And what we're gonna see is that each of the abstractions we provided give us some way of identifying them as bad. So on the left, we have the original block, which had depth 4. And so this first mutation, what you'll notice is that the new block has a depth of 2, but if you just delete the subgraph and left it as the identity, for instance, it would also have a depth of 2. So it has an effective depth of 0. And similarly for this, this second mutation. And this last mutation, it's technically deep by our definition, but it doesn't have the channel mixing that was provided by the convolutional layer. And so at a high level, the reason why our abstractions are helping is because they're essentially allowing us to identify, using static analysis, when a neural network when the mutation doesn't actually give you like a neural network. And so by performing mutations that preserve the program properties, this will bias our search towards the non-degenerate architectures. So the upshot of all this is that we can actually take large mutations in the concrete space. So we can take large subgraphs and mutate them as long as you constrain them to be small steps in the abstract space. And so I'm going to show you some experimental results, obviously, later that sort of support this claim. But first, I want to just provide one final overview of what mutations are like in αNAS, because that's really the only part of the system we're changing now that we've seen all the individual components. So our main mutation mechanism, again, goes through this sort of 3-step process. And apart from this block-based mutation, we're also going to occasionally delete or duplicate blocks as well. For the property mutations in this highlighted step, we're going to mutate the depth up and down by up to 2. For the mixing property, when we mutate it, we're just going to delete it. And the shape property, we're not going to mutate at all. And so none of these probabilities we spent much time sort of tuning. The only thing we did try was mutating the shape as well. And what we found is that you essentially just end up with a bunch of, anytime you mutate the shape, you're very likely to end up with an architecture that either like blows up in memory or leads to a dimension of 0. So we just chose to leave that one as is. And finally, I want to point out that the depth mixing properties are actually one-sided constraints on the synthesis process. So for instance, like if any subgraph is depth 2 or greater, we'll satisfy the depth property of 2. And this means that during mutations, we need to relax the constraints, otherwise synthesis can only create increasingly complex architectures. Okay, so for the last part of this talk, I promised some experimental results, and here I'm first going to start with some large-scale experiments on ImageNet. For these, we seeded the evolutionary search with some base architecture. Here it's the vision transformer. We ran alpha-NAS for 400 generations. And so this graph here on the right shows you the final population. Each of the blue dots is an evolved model, and the yellow stars, which I've also circled and drawn a red arrow to because they're really hard to see, are the original seed architectures. And so basically what you see is that not only do we find models that improve on the accuracy or the flops or the parameter count, we find models that improve simultaneously quite significantly, which sort of aligns with this intuition that the vision transformers were just slapped together, which is actually how it was done, and it says so in the paper. So let's take a closer look at some of these models now. And the first model I want to highlight maintains the same accuracy as the original model, but it decreases the flops and parameter count by almost 30%. And it turns out that this weird-looking mutation on the right here that we've been using as a running example actually occurs in the architecture. So it has almost no trainable parameters and also very few flops. And it turns out that if you apply this selectively enough, it actually doesn't hurt the accuracy while it does improve, obviously improves the flops and parameter count. And the other thing that I want to note about this is that the prior approaches to evolutionary NAS were stuck with these single odd mutations, and it would have been pretty much impossible to discover a mutation like this, which is effectively 8 mutations in one. The reason being, not only do you have to randomly discover this thing, which is pretty unlikely, but at the same time, the other thing about single odd mutations is that if the fitness ever sort of goes down when you're doing these mutations, the evolutionary line is going to be broken because you're going to be less and less likely to select it for another mutation. So another key advantage of our approaches, apart from just faster exploration, is that we're able to explore regions of the search space that other approaches would just have trouble reaching in the first place. And clearly these regions of the search space contain interesting architectures. Now, the second model I want to look at increases the accuracy by 3% with a slight decrease in the flops and parameters. And so here are 2 mutations that occur in this mutated self-attention block. I think these mutations are really interesting because, to me, at least qualitatively, they make sense. Like if some expert had come to me and been like, hey, look, I have this new optimized vision transformer architecture. I replaced a dense layer with a layer norm. I'd be like, wow, that's weird, but cool. I guess I can see how that might work. I think it also just it emphasizes the fact that by constraining our mutations using the abstract properties, you get things that just look like neural networks. So we did the same experiment, but starting from EfficientNet. And EfficientNet is a very different beast because it's already known to be highly parameter and flop efficient, and it was in fact discovered by a prior approach to NAS. And there's apart from evolutionary NAS, which allows you to sort of search unbounded in the search space, there's this other style of NAS where essentially your contribution is really focused on designing the search space itself. So you kind of avoid all these issues and you just know that your search space contains mostly architectures of high quality. And so that's how EfficientNet was done. And it was state-of-the-art for a long time, used in industry and actually deployed. And so what we found very nicely was that you can actually still improve on EfficientNet using our approach. The improvements, the scale looks a bit weird, but the scale of the improvements not actually as great as it was in Vision Transformer, as we would expect. But it's nice to know that we can still do this. And I'm not going to go into these models in depth, but there's a very detailed discussion in the paper. Also includes the same experiment, but for ResNet 50. But in the interest of time, I'm just going to move on now to some small-scale experiments that we use to sort of test the various decisions that we made in designing alpha-NAS. So for these, we ran ResNet 34 on CFAR10, and we did alpha-NAS evolution for 800 generations. And so you can see there's like tons of improvement here. There's a lot of juice you can squeeze out of this model. CFAR10 is not that hard of a data set. ResNet 34 is like way too big for it, so you can keep the same accuracy and basically cut down 96% on parameters. So one thing we did was to ablate the properties that we used, and essentially we have these 3 properties, and what happens if you sort of use like various combinations of this, like you drop some of them, you don't use all of them, you don't use any of them. And in fact, that's the one that I want to focus on here, is what happens if you don't use any properties to guide the search, and you just do these random mutations, essentially. And what we found is that as you ratchet up the size of the random mutation, as we expected, the performance degrades very, very rapidly. To the point here where you see this is like random mutations of size 3, and there's almost no progress being made. Like, yes, you do get fewer flops or fewer parameters, but like the accuracy is not improving, it's usually decreasing. So these models are not really anything great. And this is consistent also with the fact that the prior approaches that use this random exploration strategy have to use single odd mutations as well. We also compared what would happen if you didn't use progressive synthesis, but use enumerative synthesis instead. And what we found quite nicely is that you actually get very similar results. And this sort of suggests that the abstractions are doing all of the heavy lifting when it comes to guiding the search, and the specific concretization that you pick doesn't matter too much, which is nice, right? Because we don't have any characterization really of the specific concretization you get when you run progressive synthesis. Having said that, obviously the overhead of enumerative synthesis is vastly larger, and the mutations here are even smaller than what we did for ImageNet, so it just wouldn't even, you just can't use enumeration again. Finally, we did try comparing against these prior state-of-the-art approaches, and basically what we found is that we do happen to explore faster. Essentially, like you find that within the budget allotted, we find much better architectures. Okay, so just to conclude, we studied the problem of neural architecture search, and the fundamental problem there was that most legal architectures are degenerate. What we really did was we viewed architecture search as a synthesis problem and then used abstractions to guide the search. And at a high level, what I really think is that this abstract and synthesize paradigm is a powerful way of injecting search algorithms with human knowledge, where essentially you're just letting the human do like the high level reasoning about principles that might help, and then you let the search algorithm do the boring trial and error aspect. So I'm out of time now. All the code is open source, and yeah, if there's time, I can take some questions.
Wait for the mic. And please introduce yourself.
Hi, I'm Nishan, a grad student at Michigan. This is a super cool talk. This is really interesting. So in the search that you're doing, right, you have to do sort of some solving for these properties. So does that mean each evolutionary step is taking longer than sort of a more naive algorithm?
Yes. Yeah. Yeah.
And did you have slides?
Yeah. So.
What's the? It seems like it's much smarter.
So so in this case it takes about a minute. So I think these were mutations of size 3. For random mutation is instant, and then it scales linearly. So for like ImageNet, we were using mutations of size 5, so it'd be like a little over a minute. But then training takes like an hours. So it's yeah.
On the order of like what takes time in NAS, this is not a big deal.
Yeah. So training is yeah. So yeah, there was a trade-off here where essentially like if you're doing really dumb mutations, you have to be really smart about how you do evaluation. Because like Primer, for instance, used 25,000 generations of evolution to get to what they did. It's obviously not an apples-to-apples comparison, but we're able to make progress in 400 generations. So we kind of just said like whatever, just train it. But if you're doing 25,000 generations, you got to be smarter about that. Yeah. So there was this trade-off.
Hi. So nice talk. And so how difficult it was to find the distances while doing progressive synthesis? Did you find some properties for which finding the distances was hard? Do you have information on that?
Yeah. So designing the distance function is what you're asking about, right? Yeah. So depth is easy. It wasn't too hard once you started thinking about it. Like one of the nice things that I didn't mention here is that both depth and mixing, it turns out, are sort of monotonic properties in the sense that like once you increase them, they don't go down again. And then the trick just becomes like shape, you can really screw up because like once you go to a shape, you might not be able to go back to it. For instance, like there's nothing that will increase the spatial, it back in the spatial dimension. Yeah, I don't really know how to explain that. I guess like it wasn't too hard when I was doing it, but yeah, definitely that's like one of the hard things about this like whole framework, if you will.
So you think that monotony was the crucial property?
Yeah. It's a crucial property if you want to combine multiple distances. There's a subtlety when if you have multiple properties and then you want to do something that satisfies them simultaneously. It's actually the case that you might just bounce back and forth infinitely. So in general, you can't actually do that. What makes it possible in this case is that all but one of our properties are monotonic, and then we can actually combine them all. And there's a rigorous version of this in the paper if you're interested. Yeah.
Okay, the same chart again, we can take questions.